Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 81. Now, in the previous lecture, we were looking at some physical properties of planets, and I was discussing about the surface temperature and surface pressure. I want to continue with the concept of pressure, surface pressure, and atmosphere of the various planets. To begin with, I want to first add a rectification and a few clarifications from lecture 80. Okay, it is that the very first thing is a rectification. So in lecture 80, I said that the atmosphere of Mercury and Venus are thin. Okay, that was the statement I made. It was a rather vague statement. So rectification of statement made in lecture 80. The rectification is that, to see, it was that the atmosphere of Mercury and Venus are pretty thin. Now, this is a highly misleading, statement. Okay. Of course, it's partly true in the sense that when you compare the atmosphere of the real gassy giants like Jupiter, Uranus, etc., the atmosphere of Mercury and Venus are indeed thin. However, in comparison, okay, the correction is that between Mercury and Venus has a much thicker atmosphere than Mercury. Although both have thinner atmospheres this is atmosphere with respect to the gassy planets. Okay, right? I'm talking about Jupiter, Saturn, etc. There is a nice scientific fact and reason behind this statement. Okay, sorry, not this statement, this correction. Okay, this statement was correct with respect to the gassy planets, but between them there is a huge difference in the atmosphere of Venus versus atmosphere of Mercury. Let's first talk about the atmosphere of Mercury now. So the atmosphere of Mercury. Well, this is kind of a paradox because there is no atmosphere of Mercury. Okay, there is no visible atmosphere of Mercury. It's almost non-existent. You can call it almost non-existent. The reason being that Mercury is a very small planet. Now, what is an atmosphere? It is a thin envelope of gases above the solid surface, right? Or above the core of any planet. So in the case of Mercury, because the planet is very small, I'll leave it to you as a homework to figure out the exact mass of Mercury. Because the planet is actually small, it does not hold on to the gases via gravitational effects. Okay, So because the surface gravity, the reason for this is the surface gravity on Mercury is negligibly small vis-a-vis the other planets. Okay, right? So the reason is you can, of course, use your mass of the Mercury, which I gave as homework, to do one more homework also. Let's say, you can assume some thickness of various gases, right? And calculate the mass of the thickness and calculate the gravitational force between Mercury and the layer, okay, and compare it with what happens on Earth and some of the other larger planets, okay? So you can do that quantitative work. I'll just give you the qualitative reason. So the reason is that the surface gravity of Mercury is very small. So therefore, what happens is that it is not able to attract the atmospheric layer, which, as a result of the proximity to sun, right? Anyways, the sun's rays just break away the chemical bonds in the gases constituting the atmosphere, whatever atmosphere that could have been there, right? And so the gas molecules just dissipate away. So the surface gravity of Mercury is very small, and consequently, and hence, it could not hold on to the gaseous atmospheric layer. So that's why Mercury does not have any noticeable atmosphere. But with Venus, it's a completely different story. But when we discuss about the atmosphere of Venus, so the atmosphere of Venus, when you measure from the surface of Venus, it extends up to approximately 250 kilometers. With respect to Mercury, therefore, a significantly thicker layer extending up to approximately 250 kilometers right from the surface of Venus. That's the thickness of this atmosphere of Mercury. Now, what is fascinating is Venus is, of course, bigger than Mercury, but why should this be so prominent? In fact, I must also tell you that the atmosphere of Venus is also thicker than that of the Earth itself, not by much, but by some amount. Is also thicker than that of Earth itself. So the Earth's atmosphere roughly extends up to 100 kilometers, wherein you have what is called as the Kármán line, K-R-M-A-N, Kármán line, and say, above which there is, of course, the ionosphere and all those regions, but the pressure is negligibly small over there. Okay, so on Earth, the atmosphere range extends up to 100 kilometers roughly. And in fact, the International Space Station, that itself is stationed some, can you guess how much? Roughly 300 to 400 kilometers, above the Earth's surface. So Venus has a thicker atmosphere, not just vis-a-vis Mercury, whose atmosphere is almost non-existent, but it's also slightly thicker. Okay, I want to use the word slightly, that's important here. Well, what is it? What is this composed of? It's predominantly composed of carbon dioxide gas. And can you guess what else? You'll be surprised to know that there is also some amount of hydrogen sulfuric acid gas. Okay, right? So these are the two major constituents of carbon dioxide, the atmosphere of Venus. Now, isn't it amazing, right? On Earth, a lot of the carbon dioxide is actually trapped in the form of carbonates. Okay, right? So, but in Venus, unfortunately, the carbonates are not there. Okay, the carbonates are not there. So what happens is that whatever, like carbon dioxide may have been there in the beginning stage, of the formation of Venus, it all formed to the topmost layer, all as part of the atmosphere. Okay, and Venus is large enough to hold on to these gases, such as carbon dioxide and also H2SO4. Therefore, it has a significantly thicker atmosphere, right? It also, and not just that, it's so thick that it's also slightly thicker than even that of Earth itself. Please note this point. Okay. Now, this also explains, see, haven't you heard of carbon dioxide as a greenhouse gas, right? The more carbon dioxide we emit, the more our planet is going to get heated. We always keep talking about this, right? In various scientific fora, including climate change sciences, a lot of aspects which lead to greenhouse gas emissions. One prominently notorious person is carbon dioxide gas, right? So we understand that carbon dioxide is a greenhouse gas, and as a consequence, the temperature is going to get warmed up. Now go back towards the end of the previous lecture, that is lecture 80. I was giving you about some surface temperature data. Can you look at the value for Venus? What did I say it was? It was around close to 800 Kelvin, right? That was the surface temperature. You may go back to the previous lecture and check. Why is it? Now you can understand, right? It is because carbon dioxide, which is a greenhouse gas, that is getting, it's one of the reasons. It's not the complete reason. Okay. So the carbon dioxide gas forms a very thick layer of atmosphere, and so the surface is very, very hot. Okay. So now, without pontificating much, we also understand how bad it can get, right? If we keep emitting carbon dioxide on this planet, right? At some stage, the Earth's surface temperature was what? I gave it to be around, if I'm correct, I don't have the value with me now. It was approximately close to somewhere between 270 and 290. Let's say around 285 Kelvin. This was the surface temperature on Earth. If we keep, emitting more and more carbon dioxide due to what are called as anthropogenic activities. Anthropogenic refers to activities which are due to the humankind. Okay, so if that happens, of course, it would take a lot to get to this temperature itself. But there is no wonder that things will get heated up. Okay, that's it. All right. So we now understand that the atmosphere of Venus is something special with respect to the atmosphere of Mercury and also with respect to the atmosphere of Earth itself. And it is predominantly composed of carbon dioxide. And this also explains the high temperature of Venus. In any case, right, of course, the statement that the atmosphere of Mercury and Venus are pretty thin, they are still true with respect to the atmosphere of the gassy planets. For example, Jupiter, Saturn, Uranus, etc., etc. But between Mercury and Venus itself, one needs to make a very careful distinction. All right? Yeah. The next idea I want to bring forth to you is the concept of, before I go to the next idea, I'll also tell you, that the atmosphere, I've been telling you this, I'll just write it down explicitly also. The atmospheres of Jupiter, Saturn, Uranus. When I say Saturn, Titan also. In fact, okay, Saturn, Titan, Uranus, and Neptune, they easily extend all the way up to, thousands of kilometers. And so no wonder, these are actually called the gassy giants, the gassy molecules, whereas these are the rocky ones. All right? Okay. Now, having explained this to you, I also want to briefly, touch base upon the structure of the gassy planets. Okay. So this is also as part of a clarification from the previous lecture. So note, clarification about the glassy planets. I told you that the statement made in the previous lecture was that in the case of the gassy planets, the atmosphere, right? The atmosphere is almost the entire thing, meaning, the entire planet itself. I said something very similar to this. Okay. Now, while this is predominantly true, I just want to add a careful caveat. Okay. It is that a careful caveat is that, see, it has been known, or proposed rather, okay, right? Because we don't know for a fact that a planet like Jupiter, a gassy planet like Jupiter, say Jupiter, approximately, 4 to 14% of Jupiter's mass. Jupiter's mass this is coming from a 1997 study. Okay, this is caveat, by the way. So is made up of a solid core, but we don't know what its constituents are. It is still proposed to be metallic hydrogen, not exactly in the gaseous state, but not also as a rock. It is some kind of a metallic hydrogen ice-like structure. Okay, we don't know exactly what it is. Okay, so Jupiter's mass is made up of approximately 14% is made up of a denser core, which is also hydrogen, but not in the gaseous form itself. Please note this. Okay, and of course there are also some other metals which are proposed to be part of the core, but we don't know the exact details. So while the statement is definitely correct that the atmosphere is almost the entire thing, there is still a core, there is still some solid core which can contain metals beyond hydrogen also. But in any case, these are not rocky planets. So the reason why I gave this clarification is you shouldn't get an exaggerated sense, from the statement, in the sense that only gases exist in Jupiter and Saturn. Okay, no, even stuff you would expect to normally be gases, such as hydrogen, etc., they could be found in the form of tightly bound icy structure. Okay, but we don't know so many details as we speak, even in let's say about March or April 2024. This caveat, I just wanted to give it to you. Okay, all right. So this is the atmosphere of Jupiter. Next point I want to talk to you about is the structure and the atmosphere of Pluto itself. Okay, some key points about Pluto. I would say some more key points about Pluto. So from lecture 80, okay, we started our discussion on Pluto. I said that, hey, Pluto is no longer a planet because, even though it orbits the sun and it does have some amount of mass, the mass is not a constant, for various reasons. Okay, I want to build upon those statements. Okay, so from the previous lecture, from like 80, that is like lecture 80, I said that mass of Pluto is problematic. Is a bit problematic. Okay, that was the essence of what I said in last, is problematic. Well, problematic in what sense? I'll tell you. Now, it was around 1989. Around 1989, astronomical observations were made on Pluto. Okay, around 1989, Pluto was found to be closest to the sun. Well, approximately closest to the sun. Okay. So therefore, the temperature of Pluto should have been higher, in the sense that the amount of solar radiation received by Pluto would have been maximal. So therefore, it would have had enough energy to sustain the atmospheric cover. Okay. So that is the logic. So you would expect that as Pluto was moving further away and away, right, its temperature would keep decreasing. So as the temperature would keep decreasing, the atmospheric cover would keep constantly losing traction. In other words, the atmosphere would gradually, was expected to be going thinner and thinner. Okay. So expectation over the years, this was in 1989, by the way. Okay. So the expectation in 1989 was that over the years, atmospheric cover in Pluto would, I'll write it here, grow thinner. But until about 2016, this was the expectation. So this is the first, the point is, as Pluto would go further away from the sun, the temperature would become lower and lower. And as the temperature grew lower and lower, there wasn't enough energy, radiated by Pluto to sustain the atmospheric cover. Okay, so the atmosphere was expected to be growing thinner and thinner. But au contrary, I'll write down, yet until about 2016, atmospheric cover of Pluto, I'm not giving you any quantitative number yet, okay, but it grew thicker. This was surprising. This was surprising because, hey, as you move further away from the sun, you don't have enough energy to sustain the atmospheric layer. So why should it be thickening? Well, there were a few postulates. The postulate was notice that the Pluto planet, right, Pluto dwarf planet, is part of the Kuiper belt, and right next to it is the Oort belt. Okay, so when I say right next, I mean like beyond the Kuiper belt is the Oort belt of comets and asteroids and all these things. So the reason why that the atmospheric cover of Pluto got thicker when it was expected to get thinner, right, was that there were some collisions with comets which added some material into the atmospheric layer. Or another possibility, because this belt is the Pluto is anyway near a lot of comets, right? When I say near, it's in the vicinity, in the astronomical vicinity of a lot of comets from the Kuiper belt. So maybe perhaps some collisions added some layer of molecules. And B, the other thing is, whatever little solid core internally, okay, internally, the core somehow released gases. Recall, what was the density of Pluto? It was around 2. In fact, it's denser than Jupiter. Okay, right? You would be surprised by it. Okay, so Pluto is denser than Jupiter. So by some process, what's happening is that some solid state is getting transformed into the gaseous state. Some solid molecules are getting transformed to gaseous molecules. So both these imply that the mass of Pluto, because see, you also have to take into account the mass of the atmosphere. However negligible it is, right? You have to take into account the mass of the atmosphere also while calculating the mass of a planet. So the atmospheric cloud kept getting thicker and thicker when we discuss about Pluto. So these were the two reasons to be proposed, okay? But the story gets even crazier, okay? But around 2015 or 2016, this was after the NASA's New Horizon project, okay, wherein the spacecraft also collected details from Pluto. Now, this is page 9. In around 2016, it was identified that, well, there's a whole story about how was this identification done. Pluto is so far away that you need to measure a lot of aspects about Pluto when it is close enough to some other star so that you can measure the light coming out of that star. Okay, that process is called as occultation. I'm not going through the details of it due to a want of time, but you get to know that it can be such things can be studied. Okay, all right. So around 2016, it was noted that the atmospheric cover of Pluto had lessened by over 20%. Notice this. I mean, in a matter of a few years, right? What was becoming thicker and thicker is suddenly, getting thinner. Now we have to wait for measurements after a few more years. If I'm correct, this measurement was made around 2016 or 2018. I forget where, but it was by a Japanese astronomer. Okay, the cover of Pluto, the atmospheric cover had lessened by 20%. See, until now I was very careful to not give numbers, right? But here I'm confidently giving this number because it is based on the literature value. Okay, please note this. So the atmospheric cover of Pluto had lessened by over 20%. Now, as a consequence, what happened was that people were wondering about, what is happening with this Pluto? Already, its status was demoted from that of a planet to a dwarf planet. On top of it, the mass of Pluto, especially when considering its atmosphere, is constantly changing. All right. So again, this is also attributed to collision with comets, or again, some internal change. So what I've written here is attributed to collision with comets or internal change. I've written in the last line, so internal change. So the atmosphere of Pluto considers to fascinate us. There are in fact two more aspects of Pluto I want to address right now. It is that, see, despite such frequent changes to Pluto's atmosphere and its mass, okay? What is remarkable is actually that, it's core. When you assess the surface of Pluto, okay, surface has very few craters. This is a very important point. In other words, hey, despite Pluto being in the Kuiper belt, right? Despite Pluto actually being in the Kuiper belt, Pluto, while the collision with comets is attributed to be an important aspect, there is no asteroid. We can't call it meteorite because meteorite is exclusively for Earth. Okay, so there is no asteroid impacting the Pluto surface much. This is important, right? So as a conclusion, people perhaps think that this implies that there are perhaps, the word perhaps is important here, fewer asteroids in the Kuiper belt than thought earlier. All right, so these are some amazing aspects of Pluto. Now, I will continue with some more aspects of Pluto and introduce you to the early Earth atmosphere in lecture 82. I will now summarize what we saw in today's lecture. We started off by discussing the atmospheres of Mercury and Venus and how there was a huge difference. Mercury having no atmosphere, while Venus having an atmosphere which is slightly thicker even than that of Earth. Then I was clarifying about the gassy planet Jupiter and how its core, while it could contain some solids, it's not the solids, the rocky solids that you would typically expect. And then we started our discourse on Pluto and how I told you that, like we saw in lecture 80, right? The mass of Pluto keeps changing. Okay, mass of Pluto keeps changing. When I say mass, I'm talking about the atmosphere of Pluto, not the core itself. Okay, so and how Pluto's atmosphere consistently continues to fascinate us, and it's a topic of constant research, despite the surface not having any craters. So I will continue with Pluto and its neighborhood in the next lecture, and slowly move towards the significance of the Earth's atmosphere also. Thanks a lot.